How would you maximize your calendar by removing the fewest overlapping meetings? Non-overlapping intervals is a Pattern Mastery 100 favorite and a go-to at Google, Meta, and Amazon to test your greedy reasoning with intervals. Over 30% of candidates make the wrong removal choice or miss the best sorting strategy. Nail this and you'll master scheduling and optimization problems in interviews. Let's break down non-overlapping intervals using the basic approach, a proven strategy for greedy interval problems. Given a set of intervals, start, end, find the minimum number of intervals to remove to make the rest of the intervals non-overlapping. List of intervals, unsorted, may overlap. Integer, minimum number of intervals to remove. Think of cleaning up an overloaded meeting calendar. What's the smallest number of meetings you need to cancel so that no two overlap? Interviewers might ask, how do you optimize a schedule to fit as many appointments as possible without conflicts? What's tricky? Choosing which intervals to remove for minimal impact. A greedy approach, sorting by end time, works best. If you always pick the interval that ends earliest, you leave more space for future intervals, classic greedy logic. Sort intervals by end time, not start. Initialize end to -infinity and count to 0. Loop through the intervals. If the current interval start is greater than equals previous end, keep it and update end. If not, remove it, increment count, since it overlaps with the last chosen interval. Let's clarify. You're maximizing the number of non-overlapping intervals, so removal count equals total, max non-overlapping. Sorting by end time ensures each choice leaves the most room for what comes next. Edge cases. No intervals or only one, return 0. All intervals overlap, remove all but one. Sort intervals by end time. Initialize end equals inf, count equals 0. For each interval. If interval.start greater than equals end, keep it, update end equals interval.end. Else, overlap, increment count, remove this interval. Return count. Let's try to implement it using solution 1. Here we define a function called erase overlap intervals that takes a list of intervals. Each interval is like start, end, and we want to remove the fewest intervals so that none of the remaining ones overlap. We store how many intervals we have in n. This helps us size arrays and loop cleanly. If there are no intervals, there's nothing to remove, so we immediately return 0. Quick early exit. Now we sort intervals by their start time. This puts them in left to right order on a timeline, which makes comparisons easier when we build non-overlapping chains. We create a DP array called DP, where DPI means the length of the longest non-overlapping chain that ends at interval I. Each interval alone is a chain of length 1, so we fill everything with 1. We track the longest chain we've found so far in max chain. Since we have at least one interval, because n isn't 0 anymore, the longest chain starts at 1. Now we loop through each interval as the current ending interval of a chain. We'll try to extend chains from earlier intervals into this one. For each interval I, we look at all earlier intervals j before it. This is the classic DP pattern that leads to O(n)² time complexity, because for every I, we might scan many js. This if checks two things. First, intervals j1, less than equals intervals I0, means interval j ends before interval I starts, so they don't overlap. That means j can come right before I in a valid chain. Second, dpj plus 1 greater than dpi, means, if we take the best chain ending at j and add interval I, do we get a longer chain than what we currently have for I? If yes, we should update. If both conditions are true, we update dpi. So now interval I knows it can be the end of a longer non-overlapping chain by coming after j. This closes the if block. We only update when j fits before I without overlap and improves the chain length. This closes the inner loop. We've tested all possible earlier intervals j to see which ones can lead into interval I. After finishing dpi, we check if this chain length is the biggest we've seen. If it is, we update max chain. This keeps track of the best non-overlapping subsequence overall. This closes the outer loop, meaning we've computed chain lengths for every interval. Now comes the final insight. Max chain is the maximum number of intervals we can keep without overlapping. So if we have n total intervals, then the minimum we must remove is n max chain. That's what we return. And that's how this algorithm works. It first sorts intervals and sets up a DP array where each interval starts as a chain of length 1, then it checks every earlier interval to build the longest non-overlapping chain, and finally removes everything not in that best chain by returning n max chain. Efficient, simple, and elegant. Let's test our function using this input. 1, 2, 2, 3, 3, 4, 1, 3. These intervals represent time ranges, and we want to remove the minimum number of intervals so that the remaining ones don't overlap. Here's why the solution works. It finds the largest chain of non-overlapping intervals, then removes everything else. After sorting by start time, we use DPI to store the length of the longest valid non-overlapping chain that ends at interval I. In this case, we can keep a clean chain like 1, 2, 2, 3, 3, 4. These don't overlap because each one ends at or before the next one starts. That gives us a chain length of 3, but 1, 3 overlaps with 1, 2 and 2, 3, so it can't fit into that chain without causing a conflict. So the best non-overlapping set has 3 intervals out of 4, meaning we remove 4 minus 3 equals 1 interval. And that's exactly what our program outputs. 1. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully computes the minimum removals by building the longest non-overlapping interval chain, efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called erase overlap intervals. It takes a list of time intervals, and our goal is to remove the minimum number of intervals so that the remaining ones don't overlap. Time complexity, O(n) log n, because we sort the intervals first. If there are no intervals at all, there's nothing to overlap, so we return 0 removals right away. Now we sort all intervals by their end time, the second value in each interval. This is the greedy trick. We prefer intervals that finish earliest, because they leave the most room for future intervals. We create a counter called removals to track how many intervals we decide to remove. We set prev(n) to -infinity, meaning we haven't chosen any interval yet, so any start time will be valid. This variable will store the end time of the last interval we decided to keep. Now we loop through every interval in this sorted order. Each time, we decide, keep it if it doesn't overlap, or remove it if it does. We grab the start time of the current interval and store it in start. We grab the end time of the current interval and store it in end. Here's our overlap check. If the current interval starts at or after the previous kept interval ends, then it doesn't overlap, it's safe to keep. Since we're keeping this interval, we update prev(n) to this interval's end time. That way, the next interval will compare against the one we just kept. If we land here, it means start is before prev(n), so the current interval overlaps with the one we kept. When there's an overlap, we increment removals because we're choosing to remove this interval. And because we sorted by earliest end time, removing the current one is the best greedy choice. The earlier ending interval is already the one we kept. This closes the if/else decision for the current interval. This closes the loop. By now, we've counted exactly how many intervals had to be removed to avoid overlaps. We return removals, the minimum number of intervals we need to delete. And that's how this algorithm works. It first sorts intervals by earliest end time, then scans through keeping non-overlapping intervals and counting a removal whenever an interval starts before the last kept end. Efficient, simple, and elegant. Let's test our function using this input, 1, 2, 1, 2, 1, 2. These intervals represent time ranges, and our goal is to remove the minimum number of intervals so the remaining ones don't overlap. Here's why the solution works. We use a greedy strategy. We sort by end time, then keep the interval that finishes earliest whenever possible. That helps us leave the most room for future intervals. For example, after sorting by end time, the order is still 1, 2, 1, 2, since they're identical. We take the first interval, 1, 2, so prev(n) becomes 2. Now we look at the next interval, 1, 2. Its start is 1, which is less than prev(n) equals 2, so it overlaps, we remove it. Removals equals 1. Same thing for the third interval, 1, 2. Start 1 is still less than 2, so it overlaps again, remove it. Removals equals 2. At the end, we can only keep one of these identical intervals without overlap, so removing 2 makes perfect sense. And that's exactly what our program outputs, 2. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully removes the minimum number of overlapping intervals by keeping the earliest ending ones, efficient, accurate, and reliable. Quick recap time. We tackled the classic calendar cleanup problem. Remove the fewest intervals so the rest don't overlap. Breakdown recap. Conceptually, we're optimizing a schedule. From a pile of possibly overlapping intervals, we want the smallest number of deletions so what remains is conflict-free. Assess recap. We compared options and landed on a greedy strategy. Brute force is impractical here, but if we always keep the interval that ends earliest, we leave maximum room for everything after it. This directly maximizes the number of non-overlapping intervals and, by complement, minimizes removals. Structure recap. The plan was straightforward: sort by end time, sweep once, and keep an interval only if it starts at or after the end of the last kept one. Every time we see an overlap, we count a removal. The final count is the minimum deletions required. Implement recap. We implemented this flow on LeetCode and the solution executed cleanly without any errors. Check recap. We verified the logic with LeetCode's runs, confirming that it behaves exactly as expected and passes the test cases, including edge scenarios. Key takeaway: when scheduling is involved, earliest finish first is a powerful greedy pattern. By maximizing what you can keep, you automatically minimize what you need to remove.